So we're going to continue on with Chapter 12. So we're moving from the realm of heavy gauge steel construction into what's called light gauge steel construction. Okay? It's manufactured from cold sheet steel that's rolled and folded into the variety of sections that we'll talk about. I'm just grabbing a few so that I can bring them over when I need to talk about them. And there's a bunch floating around. I used to have a wall, but I guess the wall disappeared. So it's manufactured from sheet steel. The result are linear members that are very stiff and strong, right, from a spanning capability, but they're not strong in their torsional ability, right? So I can take something that's like this, and it's very stiff this way, but I can twist it really easily this way, right? And again, when I pass any of this stuff around, be really careful. I happen to have already sliced my finger open earlier today on sheet metal, so I'm particularly sensitive to it not being a good idea. But you have to be careful with it. The light gauge refers to the relative thinness of the material. The fact that this stuff is very, very thin, right? So it's not the dimensions of the material, it's the thickness of the material itself, or the thinness, right? So light gauge steel framing members, right, are produced in bulk in sizes and delivered to the site as a raw size, right? So it's not like the fabricator shop where everything's pre-cut and predetermined where it's going to go, right? It's much more like wood construction. In fact, it's called the non-combustible equivalent, right, to light frame wood construction. Now, personally, I kind of disagree with the fact that the book calls it the non-combustible alternative because it's not really non-combustible. It's very susceptible to weakness in fire because it's very thin and it can fail very easily. So I think it's a bit of a misnomer to call it that, but that's what the book calls it, right? The external dimensions of any of these pieces are designed to closely correspond to the equivalent light wood frame construction pieces, right? And so it's always challenging in this class to shift, do you cover light wood frame first or do you cover light steel first? Because they're very similar. So what I think is useful, right, is we're going to cover light steel now, and we'll cover light wood a little bit later on. And as soon as we cover light wood again, you'll remember back to the steel section and say, oh, yeah, I remember how those things went together, right? So no matter which one you cover first, the first time through is a little bit more awkward than the second time. So stick with it. You will get all the terminology down, right? Steel used in light gauge construction is coated with a zinc or an aluminum zinc. It's called galvanizing, and it provides protection against rust. So when I pass these kinds of pieces around, you'll see that it has kind of a flake pattern to it, right? That is that galvanized coating that's on it. It is that zinc. So that's what prevents the rust. So I'll go ahead and start passing that around. You guys can have an example. The coating actually varies a little bit. You can have something that's a bigger fleck pattern. You can have something that's a much smaller fleck pattern, something like this, right? But they're both galvanized. Depends on which process they use to do it. We're not going to cover that in too much depth, right? So that protects it against rust, which is obviously important, right? Because we don't want these pieces to rust out. For studs, joists, and rafters, the steel is formed into C-shaped sections, right? And so let me get a few more pieces from over here. I think this was the wall that I used to have, which was useful, but oh well. Right? So by C-shaped sections, be that, right? Right? I'm trying to think which way you're looking at it, right? So it's a C in shape. Notice that the inner edges here fold over on themselves as distinguished from a U-shaped section, right, which doesn't have those little edges. Do you guys see the difference? Right? Sorry, I don't want to stab anybody, right? You see the U and the C? Different, right? So the studs, joists, rafters are all going to be these C sections, right? The U-shaped sections are going to go at the tops and the bottoms of walls, and we'll see that in a second, right? The webs of the C-shaped sections, so by web we mean, right, this would be a flange, this would be a flange. The web is the stuff that connects them in the middle. There are punched holes, right, that are pre-punched. We can see it up here. We can see it down here. Any one of these pieces that I pick up will have those punched holes in it, right? And those are designed to be able to allow for, right, plumbing, wiring, electrical, whatever it is that you're trying to get through the walls, right, to be able to go through. And that makes it convenient right, to be able to do this because you're not having to drill through each one. And drilling through sheet metal like this is actually very challenging, right? So having them pre-punched is certainly useful, right? The top and the bottom of the wall place and headers, channel sections are used, right, or U-shaped pieces. And so this is an example of a channel section, which is just, right, a U. And so the idea is that one of these could very easily be placed in it like this. That make sense? Right? If it was the other way around, right, I would have a hard time putting this in because it has those little foldovers on the top and the bottom. Right? The foldovers are a big advantage, though, because and I'll pass these two pieces around. I know they're awkward, right? This is much stiffer than this piece, even though they have roughly the same gauge of steel, right? See, this is much easier to bend, and you should actually try to do this with these because it'll make more sense, right? So what those extra little flanges do. So I'm going to, you guys be careful, don't stab anybody with these, right? But this way you can twist them and see what I'm talking about. So the members are delivered or furnished to the site in standard lengths. Then they're cut to size on the job site, right? So we saw those pallets earlier that were being delivered to a job site, right? They're cut to size on the job site. Typically, they're going to be joined with what's called self-drilling, self-tapping screws. And there is a chart in the book, and there used to be a chart on one of the walls that had a whole bunch of screws on it, right over here. It's always interesting because this stuff moves around, right? And so it's kind of a hunt. Let's see if we have any self-drilling, self-tapping screws. There is one on here, right? It's right here, but this is probably not the best example because none of you can even see it, right? And I'll show you a picture of one in a second up on the board. Probably the better example, I'll pass this piece around, right? You can see the heads of the screws, and on the other side is the tip of the screw. The idea behind a self-drilling, self-tapping screw is it has a drill bit on one end, so you can actually drill through this material, and then it has the screw threads that tie it together. So be careful not to snag these on yourself when it passes around. Right? So here's the drawing examples, right, of the self-drilling, self-tapping screws. Right? So you notice consistently on the ends of each of these, they have a little bit of a drill bit. That's designed to get you through the sheet metal. Right? If you don't have the drill bit, if you've ever tried to do this, right, with non-self-drilling, self-tapping screws, you will find that the screws inevitably will slip out and you'll stab yourself with the screw. It's a bad idea, right? So if you get the self-drilling, self-tapping screws, big plus. So, for example, if you were going to be working on your project 2 and you were going to be using screws or bolts, right, you may consider either pre-drilling the holes and using bolts, or if you're going to screw it together, use self-drilling screws. Right? It'll make your life a little bit easier. So you want to think through those things as you work on your projects. Right? So we're going to talk about platform framing in light gauge steel. Right? So we've gone through concrete, which becomes this kind of monolithic whole, right, when we pour it together. We went through heavy steel, which takes a lot of big members and assembles them with welds and that sort of thing. And what we're going to do in light gauge steel is we're going to use a lot of little tiny pieces, and we're going to use those together as a unit to support the weight. Right? So it's a lot of little pieces that are repeated parallel to one another. Right? And so in platform framing, we're going to frame the ground floor with our steel joists, which basically means we're going to be taking pieces a little bit deeper than this. I don't have one here, right? And we're going to be laying them on end, and then we're going to repeat the process, and that's going to become our floor, right? And so these, when they're repeated on the floor, are going to be called joists. And that's the same for wood frame, light wood frame when we get there, right? After we lay those out, and in this particular example, these are actual floor joists that are used, right? They're using these as a little bit more efficient by making these cutouts because we don't really need all of that to be solid steel. They're also really good because you can run plumbing and ductwork and stuff through them, right? Which makes it a little bit easier. So those are all joists. These are laying flat. They're going to be tipped up on end, right, and stacked repeatedly. After we do that, we're going to apply basically a mastic adhesive, a glue, to the top surface of these joists, right? And we need that because we need a way to attach the wood subfloor panel to it, right? And in this particular instance, we're going to be combining, right, a little bit of wood with the steel, okay? So the subfloor is going to be laid down, and it's going to be fastened to the upper flanges of the joists with screws. So we're going to glue it, right, and then we're going to screw it into place. This is not uncommon even for wood construction. We're still going to glue it and then screw it because we don't want little squeaks in the floor. That's our way of eliminating it. That's what the glue does, right? And if you have an old house, if you walk down the hallway in the middle of the night and your daughter's down to sleep in the room, you pray that you don't step on the board that squeaks, right? Because inevitably you will. So the advantage of something like this in your house is that it would be glued down and it shouldn't squeak, right? So the steel studs are then laid flat on the floor, right, so that we can assemble the wall in an easy manner, right? After we assemble the wall, we're going to tip it up into place and fasten it to the ground, or fasten it to the subfloor, right? So the idea of doing it, right, in a flat manner is that it's much, much easier to lay the pieces out flat, right, put them together, and we're going to put a gypsum board on top of it to kind of hold them all together because they're so flimsy, right, in comparison to wood where we'd actually tip them up without any panel on them. So they're also really lightweight, which is useful, right? So we lay them out. We put that gypsum board panel down, right? And typically the gypsum panel is similar to what we would normally have sheetrock, but there's going to be some glass fibers or a mesh embedded in it to give it a little bit more structural rigidity. Once that's in place, we'll tip that wall up into place, right? Fasten it down, brace it, move on to the next wall, tip that wall up into place, and work our way around the building that way, right? Make sense? Yeah. After the wall frames are tilted up, right, they're attached to the floor and braced. Then the upper floor platform is framed, right? Similar manner, we're going to lay out our joists parallel to one another, glue down, right, subfloor on, screw the subfloor to the joists themselves, right? That's our next floor. If we want to go up multiple stories, we continue with another wall. We lay that flat down, put our gypsum board on it to keep it nice and stable, tip it up into place, right? Once we have the 4 walls done, we move on to the next floor, right? So it's a repetitive process. On the last platform, right, depending on 3 stories, whatever, 2 stories, right, we're going to end up with the ceiling and the roof, right? It's going to be framed much like a typical house with roof rafters. Rafters are the same thing as joists. They're just parallel members, but they're in a roof, right? So it's slight different descriptions for each of them. So in order to understand this better and how these pieces are used, I'm going to walk you through a bunch of drawings. And if I made you stop and draw each one of these, we'd be here all night. So I'm not going to make you draw these, but I really want to talk about the intricacies of how these things work to help you understand. And the book, for whatever reason, starts with A at the roof. So we just worked our way up to the roof, so we're going to start at the roof and work our way back down. Okay? So if we're looking all the way up here, right, at the ridge of the roof. So the ridge would be the topmost point of a roof. Obviously, in these kinds of book examples, we're going with the most basic building possible, right? So there's nothing fancy going on. We're just talking about basic framing. So the ridge is this topmost point along the roof, right? And so in this case, we have what's called a ridge beam, right, which is 2 of these C-shaped sections. Obviously, they're deeper than the ones I have, that are nested together, right? So I'm taking these 2 pieces, and I'm nesting them together like this, and that's forming, right, this ridge beam. Make sense? The advantage of putting these 2 pieces together is they're suddenly much more stable than they would be if they were separate, and it gives us a surface on both sides to be able to attach these little end clip brackets that are going to attach our rafters, right? So if I only had one side here, right, I'd have one flange, and I'd have nothing to attach this clip on, right? So we nest them like this so that we have surfaces on both sides to attach the clips, okay? Does that kind of make sense, right? This is one of the sloping rafters. This piece will repeat all the way down this side, okay? So we have a ridge beam, we have a rafter. The ridge beams are nested, okay? If we move down, and all these are out of the book, so you can go back and review them, or of course you can view them on online. So if we move down, right, to where the roof meets the second floor, okay, we're going to see the top of a wall. And so in this case, we have a stud coming up, and we have a single top plate, right? That top plate is that U channel that we have over there that's resting down over the top of the studs, right? Resting on top of that U channel is another one of these, right? In this case, it's a ceiling joist. You can call it just a joist. It's perfectly fine. And that spans across from this wall to the wall on the opposite side. So it would be spanning across, right, roughly in that line. Make sense? Okay. This rafter is coming down, having been attached to the ridge beam. Okay. And when it comes down, we need a way of attaching these two together. So we're going to do something relatively creative, right? We have one rafter that's coming down this way, right? We have another piece that would be our ceiling joist. Number one, we're going to put them together so that the webs of the two pieces, right, meet up, which gives us something to attach these two pieces together. If I can reach around this enough, right? The other thing that we'll do, and it's shown dotted here, is that we'll put a clip in that will come down and then run along the length of this U-channel that's at the top of the wall. Okay? And so that is attaching this piece and this piece, which are now attached together, down to the wall itself. So we're sandwiching three pieces together: the bracket, the rafter, and the ceiling joist. Make sense? Yeah? And we're tying that whole thing to the wall. Now, this part out here has to do with framing out how the soffit is going to be. Don't worry about it until we get to roofing. Not worth even, so just like ignore this part, right? This is the connection that we really care about in this drawing. Okay, so we move down, right, to the second floor, right here. It's in this region, right? And this is what we were talking about, right, where we have, right, a joist that's coming in, right? We have another joist. In this case, I'm guessing it's a rim joist, right, which you don't have to know the terminology of just yet. We'll get to that in wood construction. If you know joist, I'm happy, right? So we have a joist that's meeting another joist, so to speak, right? There's a little bit of a stiffener, right, that's going in here at the top of the lower wall, right? And that stiffener is basically just a piece of the wall that we've cut to fit inside the other joist. It would be like taking one of these pieces and sticking it inside here, right? Just stiffens up the corner. Okay? So these two come together, right, and help us tie this whole piece with our rim joist and our other joist here, right? The subfloor, we've got glue down first, then our wood subfloor is going on, followed by the screws that are tying the wood subfloor down into the joist. Make sense? Yeah? On top of that, we have our channel, which is over here. That's laying down on top of that wall. And then we're putting our studs inside, and those are framing up the walls for the second floor. Right? So this is going then on top of that wood framing. Okay? As we continue, right, we move down. Now we're at the bottom, right, at our foundation. So instead of having a wall supporting, so where before, right, when we were up here, we had a wall underneath with a top plate that's supporting this. When we get to the bottom, right, we have a foundation that's supporting it. We don't have a wall under it anymore, but we need a way of attaching the joist to the foundation itself. So once again, we're going to use one of these special clips that ties into an anchor bolt here, right, but also allows us to screw the joist in place. We've got the same web stiffener. We've got the same glue on top. We've got the same subfloor and the screws as well. We also have our U-channel that forms at the bottom of our bottom plate for the wall, and then we have our studs. Okay? So we worked our way back down through the building. There's a couple other slides here where we're going to move to the other end of the building, right? And this one is the most confusing circle anyway. This is in the middle of the building, but their drawings make it look like it's on the edge, so whatever. This is just showing you that if you had two joists that weren't long enough to span the total distance of the building, right, you would overlap them and let them rest on a load-bearing wall. So they're overlapping as I trip, right? They're overlapping past one another, which is allowing them to screw together, and they're resting on a load-bearing wall. Okay? I'm less concerned with the intricacies of these ones, but I'm showing them to you anyway because it'll help you understand the wood frame. All of this we will go over again when we get to wood frame because it's virtually the same. Okay? So we get down here to the foundation. Sorry, hold on. In this instance, we have joists that are running in the opposite direction because we're at the end of the house instead of the side of the house. So we have a rim joist here. We have another joist here that's spanning from this wall to that wall, right? But we need a way of tying them together and making sure they stay stiff. So we put a little web stiffener in between, right? It's like a piece of blocking that keeps those pieces from twisting, right? And so we'll put that in. Likewise, if we go up to the second floor, same thing's happening. This time we're supporting from a wall below, right, instead of the foundation. Our stiffener still goes in, right, and ties those two together so that they don't wobble. We go all the way up to the end condition, right, and this is just saying we have a rafter that comes down, right. It's kind of like a fly rafter. We'll talk about what that is in a little bit when we get to the roofing. It's coming down, providing that surface to be able to attach the outer wall to. That's enough for you to know, right? I know that that set of slides was relatively overwhelming, right, because we haven't covered this in great depth, but it's still kind of a general understanding that I'm looking for, right? So when we get to the test, the kinds of questions that I'm going to ask are going to be more related to steel. It's cold rolled. It forms into C sections and U sections. The U sections are used to accept the C sections, right? Those kinds of things. The advantages and disadvantages of steel framing, that sort of thing. It's very unlikely that I'm going to say, here's a drawing, what's a joist and what's a stud, and right, that's for the wood section, right? We'll cover that more in depth. So occasionally, right, you're going to have an opening in the floor, like you want to have a stairway that runs through or something like that. Any place that that happens, you're going to treat it just like you would up on the roof for that ridge beam. You're going to flip the two pieces and nest them together. So you have an inner surface and an outer surface, right? Happens for any opening. Right? Likewise, above a window, we need some kind of a spanning member above. This would be the window, right? The spanning member is going to be two, right, C-shaped channels. So in this case, we're taking these two channels. Obviously, these are smaller than the channels they're going to be using, right? And we're putting them together like this time, right? So we get an outer surface and an inner surface, right? And then we're going to put a U channel over the top of them, right, to tie them together. So, light gauge steel framing can be used for housing, right? Typically used for housing. The point of light gauge steel framing is that you can buy a house and own a house and not know that it's light gauge steel framing, right? It's exactly the same as if it were wood framing from a functional standpoint, right? And that's very common. Around here, most likely it's wood frame. But across the country, it varies, right? And it's going to vary based on what's the current price of steel versus what's the current price of wood, right? And so another example here, this is a multi-unit housing development, concrete first floor, so we can see the concrete foundation. The top 4 floors of this 5-story building are all steel frame, right? And so steel frame works pretty well in conjunction with heavy steel, right, for some of the structure. It's great for infill walls in office buildings and that sort of thing as well, right? The problem with light gauge steel is that it's really prone to twisting and buckling under load, right? And so you guys all saw this when I passed these pieces around. They twist really easily, right? They're not really self-sufficient, right? They work great as a unit when they're all tied together, but not as an individual member. So additional care needs to be taken in order to properly brace the structures and not have them weak during the construction process, right? And the best example of something like this is if you've ever been on a wood frame site, right? You build up to the second floor and you put your platform in on the second floor and you've got all your joists laid parallel, right? At that point, you as a construction worker can get up on the floor, right, and walk across the joists, right? Hopefully you don't fall in between them, but they're stable enough to walk across the tops of all the joists, right? And you get kind of comfortable with that. If, however, you want a steel frame building and you had all those steel joists lined up, the light gauge steel, and you went to try to walk on the top of any one of those, right, they would flop all around because they're not tied together with that platform yet. So the process is slightly different, and it's certainly something you have to be aware of in the process, right? Permanent resistance to the buckling and the twisting, right, and lateral loads is added by, right, those panels. Subflooring would be on the floors. Wall sheathing would be on the outside walls, right? That's what adds the stability to the building. So by itself, it's not that stable. Maybe we can move on, right? The other place that light gauge steel is very, very common is any kind of an office building, right, or any kind of a multi-floor setup, right? So if you're up on, the 14th floor of some building and there's partition walls, chances are they're steel framing, right? Because it has some major advantages. One, it's really, really lightweight, right? So if you think about adding dead load to a building, if you're going to build wood frame interior partition walls, they're really heavy. Wood's heavy, right? If you take light gauge steel, it's relatively lightweight, doesn't add too much to the dead load of the building. So that's a big advantage. The other thing about it is this stuff is perfect, right? It doesn't twist, it doesn't buckle, it doesn't warp, it doesn't have water in it that's going to, shrink and expand and those kinds of things. It's going to stay very consistent, and it's going to give you a really nice flat wall. By the time you put your sheetrock on it, it'll be perfect, right? And so that's a big advantage, especially on an interior, non-load-bearing partition wall. So, that being said, what do you guys think some of the advantages of light gauge steel would be? Price, potentially. Might be cheaper. More uniform, straighter. Lighter. I'm getting rid of what? Lighter on the foundation. Fireproof, maybe. Termite resistant. Rot resistant. Right? So I have a whole list of these things. Right? Light gauge steel is considered, these are the book examples, versatile and flexible. Well, I would argue that wood frame construction is versatile and flexible too, but you get the idea. It does require simple, inexpensive tools to work with. So we can get relatively simple tools, a screw gun, right? A saw with a metal blade on it, right? You could get the stud cutter to cut your studs, but it's not that fancy, right? A chop saw would do it with the right blade on it. It's not that complicated. Right? It's not like you need welding equipment or something. It's relatively simple, right? It does also provide internal cavities to run, right, your building surfaces. We haven't really gotten to building surfaces, so I'm not surprised anybody mentioned that. But we will talk about that when we get to interior and exterior finishes in about 4 or 5 weeks. But a place to run electrical and plumbing and HVAC and that kind of stuff is part of this, right? It's non-combustible. Right? Doesn't really mean it's fireproof, but it won't burn, which is good. It does weaken in fire, so you still have to fireproof it. It's significantly lighter than wood, which you guys all talked about. The other thing about it being lighter is not just for the foundation, for the weight of the building, but it's the fact that one of us could carry 20 of these, right? Versus somebody carrying 2x4s, you might be able to carry 6, right? So they're much, much lighter from a labor standpoint, easier to work with, right? They can span slightly longer than their equivalent in wood. This one's a bit hit or miss. I don't know that I would choose light gauge steel because it can span slightly longer. I would argue that if you bought an engineered product, it could probably span longer than the steel. So I don't buy it, but the book says it, so it's on the list, right? It is dimensionally stable in that it doesn't, right, change based on the humidity, right? It's not going to shrink, it's not going to expand, it's not going to warp and twist, right, which is a big advantage. What would you say some of the disadvantages would be? Condensation, very good. Heat loss. Yeah, it's a little bit of a burden to get into it, right? Potentially. Right, thermal bridge is kind of the big one. So if it's exposed to excessive moisture, it can corrode. So let's say you're building a house in Hawaii. Might not be your first choice. Right? Somewhere else, it might be okay. Okay? Thermal conductivity is kind of this big factor that's out there, right? It's much higher in steel than it is in wood. And what thermal conductivity is if there's something cold on one side, it works better with cold, right? And you grab the other side of it. So let's say I had a bucket of ice, right? And I stuck a piece of steel. It could be something like this. It could be a piece of rebar. And I stuck it into the bucket of ice, right? And I let it sit there for a little while, and I went to grab the end of that piece of steel, it would feel cold, right? If I did the same experiment and I put a piece of wood, a wood dowel in it at the same time, and I went to grab the piece of wood, it wouldn't feel particularly cold, right? That's thermal conductivity. It works with heat and it works with cold. And it's the idea that the material itself can conduct heat or cold through it, right, to the other side of the material. And so that can be a big problem if we have, right, steel on the outside of the building that passes through to the inside of the building, right? So if, say, we have a steel frame wall and that outer piece of steel is right on the outside of the building, doesn't have much cladding over it or much protection over it, it's exposed to the cold, right? We're in Alaska, right? The inside of that piece of steel, when it wraps around, is going to conduct the heat across the wall. Where, if it was wood, right, the wood doesn't conduct the heat from the outside to the inside. It would form an insulation barrier just like the insulation in our cavity would, right? So there's some challenges relation to that. So it's no surprise that we love to use it inside in non-load bearing, like inside an office building or something, right? Because we're not worried about that thermal conductivity, right? The other thing is that because of this thermal conductivity, we have a huge chance, right, that we're going to get condensation on one side or the other side, right, basically the cold side of one of these pieces. So if there's any moisture, right, it will condense on the metal, right? It's just like if you leave, a piece of metal outside overnight, right? The condensation is going to be more attracted to the metal than it would be to a piece of wood, right? You're going to get more on that particular piece. So you need to pay special attention to how do you break that conductivity, right? So you'd put rigid insulation on one side to eliminate that contact from the outside. So there's ways around it, but it's certainly something to be aware of, right? And this is where if you don't have the correct thermal break, you're going to get mold build up because you've got that condensation. It's going to deteriorate your studs. It's also going to feed the mold that you don't want, right? Light gauge steel will fail rapidly if it's exposed to fire without any fireproofing on it, right? And so the most suitable kind of protection that we're going to use, right, is basically covering it with sheetrock, right? Which is basically what we do to wood frame construction as well. But even though steel doesn't burn like wood burns, right, I would argue that a wood building, you probably have a bit longer if it's exposed to the wood than in the steel building because the steel's going to fail, even though the steel itself isn't going to burn up, right? So it's a little bit of a hit or miss. The point is you still have to cover it with some kind of a fireproof material. So typically I would give you all a practice midterm right now, but since we're having spring break and then you're coming back and then you're having the practice midterm and then you're having the midterm, right, we're going to skip the practice midterm for today, right? So you're free to go. Have an absolutely fantastic break, right? I hope you appreciate that. Oh, we'll talk about Project 2. Good. Thank you for raising that, right? Thank you guys for, or hopefully you appreciate not having any major work to do over the break. I am doing that intentionally. You deserve a break. You've been working very hard. And so the next thing that we'll talk about is Project 2. Thank you guys for reminding me before I send you out. It is very similar to Project 1, okay? This time what I'm asking you to do is to build a steel or aluminum beam, right? And I ask for, it doesn't have to be steel. A lot of times people have better access to aluminum. That's perfectly fine with me, right? Some people will have access to welding equipment, in which case they can weld these pieces together. Most of you probably won't, in which case you'll be using the other method of fastening steel together, which is bolting, right, or screwing. Nothing wrong with that. They're both equally valid. You can work in a group up to 3 people on this project. It's kind of the rare one that you guys get a group work on. The reason that I do group work is I recognize this one is more expensive than the concrete beam, right, or even the wood beam or the wood truss that you'll make at the end, okay? It needs to be a total or less than 6 inches deep. Well, by the way, this one, the goal of this is to support 50 pounds. I will run over to my office and grab a couple samples and bring them back over. 99% of them will support 50 pounds really easily. It's usually not a challenge to get that weight because if you do it correctly, the steel is such a strong material, it's just not going to fail, right? You can have no more than 6 inches in depth, right? And the thickness of any individual member can't be more than 1/8 of an inch thick, right? So you can't get a big like steel plate and do it that way, right? Let's see. Some people like to have a little bit of depth to the truss so that it's not just a single. So, for example, you could get some bar steel, right? Put a top cord, put a bottom cord, make the zigzag pattern, bolt it together, and that would suffice as a truss, right? And we will do our best to weigh that, and that's all that's really required. It ends up being a bit flimsy when you make it that way. So some people like to have a little bit more depth to it, where they'll put an L on the top, right, so that it rests on something and has a little bit more support to it. The truss that I've drawn on here is a type of truss that's called an underslung truss. It's supported by the top cord, right, so it doesn't rest on the bottom cord. It rests on the top cord and is hung that way. It's perfectly valid structurally. I would recommend making that one and thinking of that one rather than trying to set it on the bottom cord because it'll be a little bit easier for you to take a little bit less material. You're going to have to determine how to fasten the elements together. What do you want to use? It is due on the same day as the midterm, which is April 2nd. Same plan. you get 2 hours for the midterm, everybody's free to go, and you come back at 8:30, we test the beams, and then you get to go home happy, right? You'll probably bring your beam home with you because it'll probably survive, okay? I think that's it. Does that make sense? Are there any questions? I will go grab the samples because sometimes if you see the sample, it makes a lot more sense, okay? So if you want to see the samples, hang on for a second. I should stop my talking into this, and then I'll go get them.